Giovanni Di Fratta, who will talk about Korn and Poincaré-Korn inequalities, a different perspective.
Okay, thanks for introduction and thanks to the organizer for the invitation. So today I'm going to talk about the joint work with a former colleague, Francesco Solombrino, now at the University of Salento. And we say something about a different perspective. We give some different perspective about Korn and Poincaré-Korn inequalities. Okay. So the proof of the paper that we wrote together was to, well, to give a short and elementary proof of the Korn inequalities that was based only on elementary lemma, if you want. So the divergence theorem and the Q version, Q exponent version of the Ritz representation theorem. But I will tell you something more specific soon. So our approach is short. So in fact, there is just one lemma that one needs to use. It's kind of a regularity lemma, but elementary one. And is general, meaning that you don't have to change strategy to have the Poincaré inequality for p equal 2 or for p different from 2 as is used to be. And for p equal to 2 is just very simple. Just use the classical Ritz representation theorem in Hilbert spaces. And so the result, the strategy that we use works for any p. Of course, not for p equal to 1 infinity, because we know that does not hold Korn inequalities for that exponent. And for extension domains, in particular for Lipschitz domains. Okay, let me tell you first who was Arthur Korn, because somehow I was not so familiar with his history. So here is a kind of, where is it? Yes, sorry. A kind of restored picture of him while he was in Munich. So he studied physics and mathematics in, well, first of all, he was born in 1970 in Breslau, Germany. Now, let me pronounce this correctly, is Wrocław, Poland. And he studied physics and mathematics in Leipzig under Karl Neumann, where he graduated in 1890. Afterward, he spent several periods in Paris, in Berlin, in London, Würzburg. And he also benefited from the guidance of Poincaré during his time in Paris. In fact, my sources tell me that he also attended the class of Poincaré on elasticity. He was then a lecturer and professor at the University of Munich, and these photos were from the time he was in Munich. And then he accepted the chair of physics at the Technische Universität Berlin. And finally, he immigrated to the USA because of the usual climate that we know, political climate that we know at that time in Europe. And he was at professor of mathematics and physics at the Stevens Institute of Technology in Hoboken, New Jersey. And the rest you can read here. Okay, so, but which are the key contributions? It was I was not aware about. So I was only aware about his mathematical legacy in some sense. So I know that he was working on potential theory. He wrote several papers on potential theory, some massive papers about potential theory, especially the part of potential theory which is more related to elasticity theory. But I was surprised that to the general public is most known for his pioneering work in telecommunications. Because he was, in 1902, he patented the first practical apparatus for transmitting images via telegraph lines. And in fact, Arthur Korn is considered one of the precursors of television, what we use right now. And here I just put the three of the main mathematical contribution of Arthur Korn, but just to convince you that he had a great social impact with his research. Here are two extracts from New York Times, which they talk about his work. So these are two articles from 1907. And the first one is suggests that the television might be just here or two away from 1907. And in the second article, they talk about his discovery, so this his work as an engineer. Now I removed a slide which was telling something also about the family of Arthur Korn, but just say something fast. The main biographer of Arthur Korn is his daughter-in-law, which is called Teresa Korn, which was married to his son. She's, other than the main biographer of Arthur Korn, she was also, according again to my references, unfortunately I cannot give you a reference like a book where to read this, so I have to say, according to my references, was also the first woman who got an engineering degree from Carnegie Mellon. And together with this, with Korn's son, they wrote several books in engineering and mathematics together. You can find them on Amazon. You can see that there are several books from them. Anyhow, so these are the key contributions of Arthur Korn. And let's see what are Korn inequalities, so which are part of his mathematical legacy. Maybe I read better here. So, Korn inequalities is a fundamental result in mathematical analysis and a cornerstone of linear elasticity theory, because in elasticity, the displacement of a body is described by this vector field that in all the slides will be denoted by this matchable U. And the symmetric part of this gradient is what is called the linearized strain tensor, which is in some sense is a first-order approximation of the variation in distance among adjacent points in a deformation. So in some sense, if you expand to the first order the deformation that two adjacent points undergo, then you will see that by doing a simple Taylor expansion at the first order, what comes into play is just this symmetric part of the gradient. And the inequality that Korn was trying to establish, and in fact established in these papers that he published at the beginning of the previous century, were in some sense to match the approach elasticity based on forces to the variational one. So he wants to give a kind of formal and rigorous justification of some variational model of elasticity which should match with the you see what we now call the Lagrange equation, so that with the PD arising from the first order variation. And in order to make everything rigorous, you need this Korn inequality. And the one that you see here is, you see, it's a kind of a regularity inequality, because it says that if you can bound the gradient of the displacement, the whole gradient of the displacement, just by knowing just the symmetric part of the symmetric gradient. Now, if you want intuition about this, you have to think like that the symmetric part of the gradient is just measure changes of length, volume, and volume, while the anti-symmetric part of the gradient is more related to rotation and the translation in space. So in some sense, it's reasonable that if it's really this is the case, then apart from where is located the body, you must control this quantity with just this quantity here. Okay, every one of you knows that this is a fundamental result in proving existence, uniqueness, stability, our solution to problems in linear and nonlinear elasticity. And this is also called the second Korn inequality, this one. Second Korn inequality because it solves for every U which is smoothed up to the boundary. And so to distinguish from another Korn inequality, which involves just functions which are smooth and with compact support in the domain, this other equation, this other relation that you see is usually referred as the first Korn inequality, or Korn inequality of the first type and of the second type, as you wish. And but the second one is here is really, how to say, nowadays it's really easy to obtain it, because it just follow from this equality that you can check by integrating by parts. It's just integration by parts. You get this equality, and you get that this constant here in the first Korn inequality can be taken too. So independent even from omega. This is a general fact, but I don't want to, just by scaling argument, you can see that you can always find a constant that does not depend on the domain, the geometry of the domain. Okay, so let me tell you why a different perspective. Well, because Korn original proof of the second Korn inequality, while the proof of the first Korn inequality, as I show you, follows by that equality that is quite easy to derive, even if we are talking at the beginning of the previous century. For the second Korn inequality, the original proof of Korn was really complicated to the level that also Friedrichs, that I will go into cite his paper later, claimed it was very complicated, this proof. Now, subsequent proof of the Korn inequality, especially for general exponent P, are also very technically involved and use Calderon-Zygmunt estimate, the singular integral operator, and so on. And in fact, I reported here something that you can find in the paper of Friedrichs. The paper is the following one on the boundary value problems of the theory of elasticity and Korn's inequality. And it says that the second Korn inequality, the proof of the second Korn inequality given by Korn, is, in the word of Friedrichs, very complicated, to the level that Friedrichs himself, to admit, he was unable to verify Korn's proof for the second case. The reason for that, according to Friedrichs, other than the length of the involved argument, was their nested structure. The proof given in Korn 1909 refers to previous results presented in Korn 1908, which still refer to early papers of Korn. So, given direct proof of Korn's inequality, in the second case was one of the main aim of this paper, famous paper of Friedrichs. Okay, sorry, it was not. Okay, let me give you a brief review of a century of research on this topic. Of course, I will give you just the more influential milestone on this on the proof, on various proofs that arise of Korn inequality. All the references that I'm going to give you in this slide are for p equal to 2. Okay, so for p equal to 2, there is the original proof of Korn, which was, I already told you, claimed to be really compressed by Friedrichs. Then there is this work of Friedrichs in 1947, so almost 40 years later. And in this paper of Friedrichs, motivated by the complexity of Korn's work, he gives still a technical proof of the result, still that holds just for p equal to 2. For a class of domain which is not so general, he called these domains omega domains. And under the additional assumption that the displacement, in some sense, is rotational in the average. So there was this additional assumption in the Friedrichs paper. In 1962, Gobert extended the result of Korn to more general domains, and also removed this assumption on the fact that the curl of the displacement must be null average. In 1981, maybe this is a quite well-known niche result. He gave another proof of constant second inequality, and also was labeling the original proof of Korn like doubtful. And introduced an alternative argument based essentially on these extension operators. The first simple proof was given in 1989 by Kondrachev-Olenik, but still in the case p equal to 2. And finally, I want to mention this paper of Charlie 2010, in which he gives another proof of second Korn inequality based on the distributional version of San Venant lemma. And in the same paper, if you read, he says that there is also a nice proof in Dutré-Lyon of second Korn inequality, but still that this proof that you can find in Dutré-Lyon is based on what he refers to as a remarkably difficult to prove lemma with Jacques Lyon. If we go to general exponent P, the situation is even worse. The first result in this direction were from Miklin, Moslov, and Jasnikov. I hope to pronounce this as well. And a simple, again, and self-contained proof of the general case is given in another paper of Kondrachev-Olenik, but still is not elementary to read. It's not something that you can teach in 1 hour lecture. Well, what I'm going to give you is something that in 1 hour lecture you can explain to someone. Okay, so I was telling you, what about p equal to 1 and p equal to infinity? This is well known that the Korn's inequality do not hold. For p equal to infinity, it's easy to construct examples, but for p equal to 1, you have to rely on some other result. At least the standard way that I know is to rely on this result by Ornstein. And our proof is based on essentially on Ritz representation theorem, and I will tell you better what I mean by, there are many Ritz representation theorems, so I have to explain you what I mean exactly with this, by this. And the class of domains to which it holds, well, for the first Korn inequality holds on any open set. So as soon as you are interested just in the first Korn inequality, we can let it work on general open set. Even if it's unbounded, we have in some sense, you can introduce a weighted version of it. But for the second Korn inequality, which is the most difficult one, you have to assume something on the boundary. And our proof works for extension domains. So in particular for each domain, but even for epsilon delta domain in the sense of Jones. And if I'm correct, there is a counterexample of Girardi, which says that a counterexample of Girardi, which says that there are some open set with the Korn property, or with some open set for which the second Korn inequality does not work. That is for sure. Now I don't remember specifically which kind of open set was built. If it was without second property, I don't know, something I have to recheck. But in the paper, I really went through all the literature, and so you can find them the precise reference. Okay, let me tell you a little bit about the roadmap. So the strategy, why is different? Because we first prove Poincaré-Korn inequality, which are not Korn inequalities. And Poincaré-Korn inequalities, we can really derive this by vector algebra and divergence theorem, just these two ingredients. And we get Poincaré inequality that in the next slide I'm going to show you. If there will be time, I will give you a sketch on how to prove these Poincaré-Korn inequalities, but otherwise what will be in the next slide will just be assumed to be true, okay? And trust me, it's really elementary to derive this Poincaré-Korn inequality. At least was in fact, was how the paper originated. We found this elementary proof of the Poincaré-Korn inequalities, and then from this you can understand the functional setting, the correct functional setting, and then use Ritz representation theorem plus open mapping theorem, and you get Korn inequalities. Okay, let's start with Poincaré-Korn inequalities. Yes, so the first version is for any open set. So, and this is the inequality that you see here. Essentially, the Poincaré-Korn inequality bounds the LP norm of the displacement through the a weighted version of the LP semi-norm of the symmetric gradient of the displacement. It's a Poincaré inequality with the symmetric gradient instead of the classical gradient on the right-hand side. And due to the weight that you can see here, this inequality holds for every, no matter if the domain is bounded or not. Okay. And here we are, sorry, I have to tell you this, here for every u which is in infinity with compass support. Okay. Well, as a corollary, you get what is the one that everyone knows, so the classical Poincaré-Korn inequality, because if the domain is bounded, you can always bound this guy here with the diameter of the domain, plus something, it doesn't matter. And so you can absorb everything in a constant here, and you get this inequality here without the weight anymore. And if you do the same strategy, so use the divergence theorem and then vector algebra and then divergence theorem, you can always obtain a version which works for functions which are infinity up to the boundary. Of course, now there will be a boundary term, and you have to assume that you can use divergence theorem. So you have to assume that, for example, the domain is Lipschitz. Okay, so these are the Poincaré-Korn inequalities, and will be our basis to prove Korn inequalities. Okay, now that we have these Poincaré-Korn inequalities, we know, how to say, we think like we are in at the beginning of the last century, so we don't know that these spaces already exist and so on. In fact, I'm using actually the notation of Teman, but let's think that this stuff does not, we are not aware of this stuff, so we just know Poincaré inequalities. we introduce this space, which is usually denoted by E, I guess by for elasticity space. And this is nothing but this E1P is just the space of distribution in LP whose symmetric gradient is still in LP. This is easily seen that this is a Banach space when equipped with its natural norm here. And as usual, if you put a small zero not on the subscript, this means that we are considering the closure of the space of a smooth vector field with compass support in the space E1P. And this is sometimes referred as the first elasticity space E01P. Okay, so the acquired Poincaré inequality, let you note that the acquired Poincaré inequality in the previous slide tells in particular that the gradient semi-norm on this first elasticity space is actually a norm. Okay, like it's same strategy of classical Poincaré inequality. Poincaré inequality tells you that the classical gradient semi-norm is actually a norm in the space of W01P. And now the idea, what is the idea? Is that if you want to prove the second Korn inequality, you just have to prove this regularity result here, so that the space E1P and the space W1P are equal. And if you want to prove the first Korn inequality, then you have to prove that this space here is equal to W01P. Why I say this is a regularity result? Because one inequality is trivial. So it's trivial that if you are in W1P, you are also in E1P. You just have to prove the reverse inequality. And after this equality, I established the equivalence of the corresponding norms. And so the Korn inequalities, first and second, will just be an application of the open mapping theorem. But I will go step by step until there is time to see if I can convince you that we have a proof of it. Do you want me to repeat something? Because maybe the notation is, I hope is clear, otherwise interrupt me because we have time. So the linchpin of the proof is this regularity lemma, which essentially says that if omega is a generic open set and p is between 1 and infinity, then a function whose symmetric gradient is in LP actually is as the whole gradient in LP, at least locally. So, summarizing this this inclusion holds. Okay, this is the regularity lemma. And I give you a proof sketch for n equal to 3. Actually, it's the whole proof for n equal to 3. And for n equal to 3, because for n equal to 3 I have the car operator, so I don't have to introduce other notation for you. Otherwise, in the paper I have to introduce some operator which comes from the anti-symmetric part of the gradient, and it's exactly the same. It's just a matter of notation. So assume that U is in this space. You want to prove that it's in W1P log. So what you do? You take a ball which is inside omega, and you consider this distribution here, the one that to every phi associate this quantity. This is actually an element of the dual of W01P because it's something which is clearly continuous in this space. Yeah. And so if suppose that this is W012, then you know that by classical Ritz representation theorem, this is a bounded linear functional on W0 on H1, and so you have a Ritz representative. So something that does this job. This is what it means to have a Ritz representative. You are representing this functional with respect to the scalar product of the space W01P. Okay. Now, if P is not equal to 2, the result still holds. It's called the Ritz representation theorem, and essentially says that every element of the dual of this space is still in the image of the Laplacian. So you can represent this as the Laplacian on something, or Laplacian on something which is still has a regularity, the right regularity is in W01Q. You see, when P is equal to 2, Q will be 2 as well. It's just the harmonic conjugate of the exponent. So I put this here, but what I'm saying is that since U is in this space here in W01P, there exists a distribution V whose Laplacian is exactly that guy, and you can say more that the distribution is distribution Laplacian of a guy which still has some regularities in W01Q. Well, if you do a little bit of algebra, really a little bit of algebra, you see that the relation that is written here, or if you want this relation here, is actually equivalent if you want to get rid of the symmetric part, so this sim and as subscript, is equivalent to the equation in the sense of distribution of Laplacian V is equal to Laplacian U plus grad div of U. Well, but once you have this, if you take the divergence of both sides of this equation, what you get? You get Laplacian of divergence V equal to Laplacian of divergence U plus divergence of gradient, this is the Laplacian. So plus Laplacian of divergence of U. So what you get is that the divergence of U minus V over 2 is harmonic. And if you do the subjob taking the curl of both sides, you will get the curl of U minus V is harmonic. But harmonic distribution of Wyatt's lemma are C infinity. And so you get that these two guys, this divergence, and this curl are C infinity function on that board. Use Hodge decomposition, which in R3 is really simple. The Laplacian minus Laplacian is equal to curl minus grad div. You decompose like this, and from what we get here, you get that this quantity here is in C infinity. And what you get here, nothing, you leave it like it is. This is something like which is in W minus 1Q prime. I remember you the notation because I don't know if it's really, I suppose it's really standard. So by this I mean the dual of the space W0, 1Q. Okay? So if I have to denote the dual of W0, 1P, I pass 1 to minus 1 and then I put a prime close to the exponent. Okay? So what is written in here, where is it here, is the dual of the space W0, 1Q. Okay? Here, when I said it was in the dual, was a continuous linear function on W0, 1P, was an element of W. Okay, 0 here is wrong, is just a typo, there must not be any 0 here. So it's an element of W minus 1P prime. Okay? So, long story short, since also the Laplacian of V is in the same space, you get that minus Laplacian U is in the space W minus 1Q prime.
The identity in 2, the one where you relate the Laplacian with the gradient, you get it from algebra?
From this.
Ah, okay, from the algebra of the weak form.
Here.
Okay.
In fact, you can see because Laplacian here is this will be this will be minus curl of U, what is written here, and then there will be let's see, this will be plus grad div of U. So there will be 2 grad div of U here, and then there will be left curl of U. But when you take the divergence of the curl will be 0 in the sense of distribution. You will just get this part equal to this part after the divergence. Okay. Well, plus with the 2 here. So what's the relationship? Second? What is the relation between?
P and Q, the exponent.
The conjugate exponent. So P1 over P plus 1 over Q is equal to.
Prime also.
Second?
Q is equal to P prime.
Exactly. Q is equal to P prime. Yes. So we are here. So what we derived is that if U is in E1P omega Rn, then the Laplacian of U is in W minus 1Q prime of a ball, of any ball which is inside the omega. But again, you invoke this Curie's representation theorem, and this means that this guy is in the image of the the Laplacian of NW01P function. So there exists a W01P vector field W such that the Laplacian of W is exactly equal to the Laplacian of U, because this is an element in this space. An element of this space is the Laplacian of something which is regular. So overall, you get that U is in C infinity plus W01P Vrn, and this is included in W1P log, because unfortunately we cannot go up to the boundary here. Okay? So this can be something which is not integrable C infinity on the ball. Well, okay. Depends on the ball. Where is the ball? If the ball is close to the boundary, we have a problem. Anyhow, so this is the regularity lemma. And now how you can reach the second Korn inequality, for example. I thought it's just elementary functional analysis. Because, well, what we proved is the regularity lemma before. Now what we're going to prove is this equality which from open mapping theorem will give us the result. So one inequality, one inclusion is trivial. We don't have to do anything. We have to prove this other inequality here. So we take an element which is in E1P omega with omega an extension domain. We extend this function in this space to a function U tilde which is defined in hula of Rn. By the acquired lemma, this will be in W1P log of Rn. And so this will be in W1P omega. That's it. So this shows this equality here. After you have this equality, the equivalence is just open mapping theorem because if you consider the injection of W1P in E1P, well, this is for sure continuous injection. But we just proved that it's also surjective. And by open mapping theorem, every surjective continuous linear map between Banach space is an open map. And so it's actually, in this case, an isomorphism of W1P in E1P. And so one inequality, you see, one inequality, this is less than equal than this guy here is trivial. But now that we know that two spaces are isomorphic, we have also the other way around in the norm. Okay. Second. Second.
With a constant appearing. Yeah.
When you say this is less than equal than something, yes. If I remember, for p equal to 2, there is no problem, there is no constant, but for general p, you need the constant there. Yes, okay. Anyhow, for the first Korn inequality for general p, the strategy is actually the same. I'm not going to give you the strategy, it's just a minor difference with respect to the proof for the second Korn inequality that I gave you. In the paper is there the proof, but it's really elementary as well. And yeah, okay, this time, so I show you this, that because maybe you don't trust that we base everything on the Poincaré-Korn inequalities, and I told you that it's really elementary, just vector algebra divergence theorem. And I give you the idea, and then I give you the precise proof for another case, which is simpler, because it's just difference in the algebra that you have to do, not in the methodology. So the idea is that there is if you denote U epsilon as a couple U and epsilon, so this is a vector whose first 10 components are the components of U, and the last one is just epsilon, then the following equality holds. So that this guy that you see here is equal to this term that we like because there is a gradient sim of U. This other term which also we like because we can bound with the gradient symmetric part of the gradient, plus the divergence of something. Now, if I integrate on omega both sides, well, this part disappears because it's the divergence of something, and I'm assuming that the function of U epsilon is infinity with compass support. So this part will disappear. And if I take then the limit for epsilon goes to 0, the norm of U epsilon will go to the norm of U. And everything will give you directly this, this inequality that is here. But I want to give you a special case of the idea, because the idea comes after I was working with a colleague in Naples, Alberto Fiorenza. We were applying this technique of the divergence theorem quite successfully in a different setting. In fact, this idea of the divergence theorem also works if you want to prove Hardy Poincaré inequalities, both in classical and variable sublet spaces, so even when the exponent is a function. And let me give you convince you that this kind of inequalities, if you use divergence theorem and algebra, are really easy to prove. So suppose that you want to prove this Poincaré inequality. So look at the generality. We are saying that for any u which is in W0 1p, or if you prefer in C infinity compass support, if the domain is bounded in some direction, so it can be also unbounded like a strip, the important thing is that the domain is bounded in one direction, then the LP norm of a function of u is bounded by the derivative of u along that direction in which the domain is bounded. And how can you prove this? Well, first, by density, just assume that u is C infinity with compass support. Assume that p is greater than 1 at the very beginning, so that you know that if you take the modulus of u to the p, this is a function which is still compass support, but also C1. The critical exponent is p equal to 1. But if p is greater than 1, then this guy is C1, so it's fine for us. Oh, where is it? Just to shorten notation, the x minus 0 denoted by this function tau. What you do, you just compute the divergence of this quantity. If you what is written here is really divergence of x minus x0 dot into sigma multiplied by sigma, everything multiplied by the modulus of u to the power p. You expand this divergence here, and you get that this divergence is u to the p, u to the power p, plus p, which multiply the sine function of u, u to the p minus 1, and derivative with respect to sigma to u. Well, you integrate both sides in omega. The divergence theorem says that this guy vanished. And so you get that the integral of modulus of u to the p is equal to the integral of what is written here. Well, but this guy tau x0 dot sigma, I could even forget about that. I just put to be precise, but this is, you can just bound with the supremum among all x which are in omega, if omega is bounded in the sigma direction, of tau x0 dot sigma. This is something which is bounded if the domain is bounded in the sigma direction. Okay? So this quantity here is finite if the domain is bounded in the sigma direction, and then use just Elder inequality. So you get u to the p to the 1 over q, and d sigma u to the p to the 1 over p. But here you have to the power 1 minus to the power 1 over 1q, you get 1 over p. So you get exactly what is written here. And then by the arbitrariness of x0, the point x0, that you can choose whatever you want inside the domain, outside the domain, it doesn't matter at all, you get that you can take the constant in this way here. Okay? This works for every p greater than 1. But now that you know that this equality holds for every, now that you know that this inequality holds for every p which is greater than, where is it? Here. Every p greater than 1, since you know that the constant does not depend on p in a dramatic way, you can just take the limit for p which goes to 1. Because what is inside the integral is smooth function with compass support. So it's regular at least. So you go to the exponent p which goes to 1, and by either by dominated convergence theorem or monotone convergence theorem, you get that also the case p equal to 1 holds. Okay. So the equality also for p equal to 1, and the same strategy works for the case I was telling before of the Poincaré-Korn inequality. The difference is that for classical Poincaré inequality, you are working with the scalar function, while for the Korn inequality, you have to work with vector value function, and you have to do a little bit of vector algebra. But we are talking about half page of computation. That's it. Okay, and I think I'm done. So yes, thanks for the attention.
Right, questions?
Can I make a historical comment? So related to the historical introduction. So there's something that really caught my attention because it seems that it was the proof of Korn's inequality that got Calderon the job in Chicago. So Calderon was particularly notorious for doing, of course, very important work, sometimes forgetting about it and definitely not publishing it. So when he was still in Argentina, he actually did a proof of Korn's inequality, and somehow he casually sent it to somebody in a letter and forgot about it. So, and then he was invited to visit Chicago, and well, the first research meeting they had, I believe it was Sigmund that present his proof of Korn's inequality. And then he says, by the way, there is a second proof that you might find interesting. So, and then he reproduced Calderon's proof. And Calderon said, oh, this is really good, this is really interesting. So, and that's really when he got established and emigrated to Chicago. So, so there's very interesting things about Calderon. For example, another thing that, if you allow me, another thing I found out that I found particularly amazing is that he never published his work on tomography. The first work on tomography and the first problems, he never published it. But now if you look for it, you're going to find a paper, I believe it is maybe 2003, so it's not possible that it was written by Calderon. And then what you see is that he gave a lecture in Rio de Janeiro where he presented his first results in tomography. Somebody took notes, and then later, they decided to publish his notes, those seminar notes. But somehow I had the feeling that the person who took the notes, I don't know if he really understood very well what was going on, so a lot was lost in translation. And, well, if you want to know details about the exam, you may be missing many things. You should contact Gunther Ullman. So Gunther Ullman is very much on top of this history, and actually he told me just a few months ago that they were actually trying to get the tomography work corrected and published again somehow, because right now it's not, if you don't guess what's really going on there, you actually miss a lot of it. So
thanks
I like
a lot.
your historical presentation. That makes a lot
that was quite fun for me to I was quite enjoying to look for info about Arthur Korn. It was not so easy actually. It's not like if you type Poincaré, you find everything. But for Korn it was not so easy. That's why I enjoyed it.
Around Calderon, you.
At least I wrote that they use Calderon-Zygmund estimates. That is, at least I wrote that they use Calderon-Zygmund estimates, so that names appear in the slide. But I didn't know that there was a proof by them.
It all started with that visit.
Okay.
Yeah. So, when you do finite elements and you think about the Korn inequality, if you have a conforming finite element discretization, you inherit it from the continuous one. But if you have
I cannot hear you very well. Say again.
So if you do finite element, you do finite element discretization of an elasticity problem. And you want to Poincaré inequality to prove the well-posedness through Searle's lemma. Now, when you do that, you usually inherit the Korn inequality from the continuous Korn inequality. But if you have very common finite element spaces, like the Cruzier-Rabiat finite element spaces, you don't have the Korn inequality. The Korn inequality doesn't hold there. You have counterexamples. I was wondering, if you do the analogous of what you did in a discrete setting, you should retrieve the same proof, right? Which step fails in the discrete setting for a Korn?
That I cannot tell you. No, that I don't know, because I'm not so familiar with this discrete setting. I worked in the past, but not at the level that I can answer to such a specific question. It's easier if you go through the paper and if you have more familiarity with this, you see if the argument breaks or not.
Well, it does break because there is a counterexample.
Yeah, so it breaks. So.
Any other questions? So I actually have one.
Okay.
So there are these kind of more, quantitative versions or of Korn's inequality where you say you're given an arbitrary vector field, and then you can estimate the skew symmetric part by the symmetric part and a curl term of the vector field, which is, if the curl is 0, then you basically recover Korn. So there's quite a few works. I mean, there's these things by Gmaileder, specter, and there's various combinations of people working with this. I wondered if your proof actually gives something like that as well, because it would be interesting to have those versions as well. They're almost like rigidity estimates,
Yes.
so linearized, of course.
As well, because also the reviewer was asking
Because
us.
I saw the curl come up in your proof, right?
Yeah, also the reviewer was asking us this question, but
it wasn't me.
was not no, but was not so. It's not so easy to investigate this other part. It's another paper, okay? But the idea that we were thinking a little bit, Francesco and I, about this, and we are almost sure that one can adapt what we did to these other situations. But the algebra is start to be a little bit complicated. So it's not that you can. But the algebra is going to be more complicated. It's not a matter of the methodology. And so we were also thinking that the paper would have been better if it's something clean and that everyone can read. Otherwise, maybe someone can be lost in the paper. But yes, we know that we can do something in this direction.
Okay, thank you. Right, I'm in negative territory with the time, so if there are no further questions, then let's thank the speaker again.
Thanks a lot.